All right, we're working on preparation 23, and we are going to try to solve this example problem and another one from the video Intro to Linear Programming by Joshua Emanuel using Excel. So here's the problem. We have 4 decision variables, so I'll write out my decision variables. We've got an x1, x2, x3, and x4. We're going to have the left-hand side of the constraints and the objective function and the right-hand side of the constraints. The coefficients of the objective function, which we're trying to maximize, will go down here and the constraints will go below it. But first of all, our decision variables will start off with zeros in all of their places. We're trying to maximize 217 times x1, 125 x2, 88 x3, and 109 x4. And so we evaluate the left-hand side, or the objective function itself, by taking the sum product, dot product of these and these here. I'm going to lock these cells, so that I can click and drag that down because we're going to need it. We've got constraints. We need a less than or equal to constraint, and it has coefficients 58, 44, 26, 23, and we will copy this down. And this should evaluate the left-hand side of the constraint for us just fine. And the right-hand side is 120. I'll copy the rest of the elements. Okay, so here's our spreadsheet. So we go to Data, Solver, let's set up Solver. Okay, our objective cell is right here. We want to maximize it by changing the variable cells. These are our decision variables subject to constraints. We need all 3 of these to be less than or equal to the right-hand side. The left-hand side is less than or equal to the right-hand side. And we know that our decision variables are all going to be binary. So we select bin for the constraint type. We need to select the decision variable cells directly. This automatically makes them positive and between 0 and 1 and exactly either 0 or 1. We say OK. And it doesn't really matter whether we make unconstrained variables non-negative because we've got the binary constraint there. We want to choose simplex LP. And then in options, you're going to want to take note of this. It says integer optimality percent, 1%. This is how close it is to the optimal solution. We want within 0% of the optimal solution. It needs to be exactly optimal. We do not want to ignore integer constraints. Go ahead and leave all the rest of this just as it is. So all methods, we want an integer optimality at 0%. We say OK. And finally, we solve. And keep solver solution, OK. Notice 1011 matches what it has here, and 414 is the optimal return. We got it right. I'm going to zero everything. 0, 0, 0, 0. Had we gone into solver and clicked options, had we left this at 1% and solved, we might get the correct solution, the optimal solution, but that's not guaranteed to be the case. The reason for that option is to save time, and get you close to the optimal solution, but it might not get you the exact optimal solution. So that's why we set it to 0 typically. Next, let's solve the second example from the video. So I'm going to copy over this information just in the format it's in, so we'll see how we might set this problem up without having to create an explicit linear program ahead of time. So I'm going to create some cells for the decision variables. We've got our xi cells, the number of units that are produced on each machine. So we'll start out at 0, 0, 0, and then the yi decision variables will also all start out at 0. We're not using the machines at all. And what are our constraints here? So we'll have one constraint that is going to be the total number of units produced, and that's just going to be the sum of however many units I produce, the xi's. This is units on a given machine. This is whether the machine is used. So we're going to have to put a constraint on that. That total number has got to equal 1,000. And then we also have capacity constraints on each machine. So machine 1's capacity constraint, machine 2, and machine 3. And so as it explains in the video, here we're going to have that the number of units produced on the machine minus the total capacity multiplied by whether we're making units on the machine at all is less than or equal to 0. So I don't put the less than or equal to 0 here. Let's evaluate it. So this means that, let's say we're saying it's less than or equal to 0. So if I make units 300 and I had this left at 0, which would be incorrect, we have to make this a 1 if we are making any units at all, then this would be greater than 0. That's not okay. If we say that this is 1, that's fine. We still got 100 left that we could make. If we make this 400, we're still okay. We're still within bounds. We could say we're going to use the machine, but we're not going to make any units. That's fine. This is still less than 0. But if we said, oh, we want to make 500 with the machine, then this goes greater than 0. That's not okay. All right. So we're going to do that for each of the machines, a similar constraint. And I'll set this to 0. Okay, so we go into solver and our objective function cell. Oh, we forgot to do that. So let's go ahead and include the objective function. The objective is we want to maximize. We have the fixed costs, and those are going to get multiplied, the sum product really of the fixed costs by whether the machines are used. Plus we have the cost per unit, well, the sum product of the cost per unit times the number of units made by each machine. So that's our objective function, and we've got our constraints. So go to the solver. Our objective function cell is right there. We want to maximize it, or excuse me, we want to minimize this because we're trying to minimize the total cost by changing the variable cells. Well, all of these are variable cells. So it turns out we can select a two-dimensional array of decision variable cells. We have the constraints that all of these numbers, well, let's see, this number here has to be equal to 1,000. We have to make exactly 1,000. And we're going to add another constraint that these cells here, these capacity constraints, are less than or equal to 0, all of them. We also have integer constraints. We have that these cells here are integers, and we have that these cells here are going to be binary. And I think we should probably add, for good measure, probably want to make sure that these cells are greater than or equal to 0. Could probably do that. Let's forget that for a second. I'm going to say cancel, and I'm going to see if that was necessary or not. So we've got all our constraints. Even though we say make unconstrained variables non-negative, because we've constrained these to be integers, that might not work for us. So I can go to simplex and we solve. So it looks like we didn't need to explicitly put that constraint on there. If the optimal solution turns out to be that they are positive, then we have no problem. We don't have to go back and add that constraint. I just want to, the solver found the solution. I want to say, okay, I'm going to go back into the solver and I'm going to check the options this time. So this said 550, 450. Let's see if we change this integer optimality to 0, as we should, to ensure that we get the optimal solution, the global optimum, see if it changes anything. And it took a little bit longer that time, but it still finds the same solution. Let's see if this is what he gave in the video. And yep, that's the optimal solution in the video. X1 and Y1 are 0, 550 and 1, and 450 and 1. And then the objective value, well, we presumably got that right at 3090. Now I've started to clean up the spreadsheet a little bit, indicating that we've got the left hand side of the constraints here and the right hand side of the constraints here. And I realized that, you know, the way that we wrote the machine capacity we had to recreate the constraint from scratch every time, when really it would have been nice if we had arranged these along a row. So I'm going to show you how we might do that. The capacity constraints, these are all less than or equal to constraints, or less than or equal to 0 is what we're going to write here. We could have said that we set up the first one. It is the number of units that a machine produces minus whether the machine is used or not times its capacity. We could have written it out like this. And we want to make sure this is less than 0. Well, we could have clicked and dragged this over like that. And then we wouldn't have had to create these constraints like that. So I'm going to delete that. So let's go ahead and use the solver. Now we'll see how to fix things. I'm going to delete the constraints that were there before, and I'm going to add them back. I'm going to say add that all of these cells, these capacity constraints, have to be less than or equal to 0. And we say OK. Double check our options, integer optimality 0%, OK, and solve. And the solution doesn't change at all. It was just a different way of laying out the spreadsheet that would save us a little bit of work in setting up our equations. And so this, again, this is not the most formal way of doing it. It's not a very good way of presenting it, but if you need a quick solution to the problem, sometimes just using the layout of the data as it's initially presented can lead to fast ways of creating the spreadsheets.